Welcome back to the Math Professors, and today I'm going to cover volumes using cylindrical shells. Now we've done volumes of revolution using the disk and the washer method, but there's another method that's pretty common, and this is called the cylindrical shell method, and some people call it like the onion method, and you'll kind of see why that's called this in just a second here. So what we're going to do is look at a function that looks like this, and what I want to do is I want to spin this about the y-axis. So spinning this about the y-axis, it's going to give me something that looks like this. So we can kind of see it's like a bowl, and what I have is I'm going to have volume here with some kind of empty space here, which is why I'm kind of calling it a bowl. And the way we were doing it before is we'd slice, perpendicular to the axis of revolution, and then we get a bunch of disks or washers, depending if there's like a hole or if there's not a hole. So if we were using the disk method, and I'll erase this soon, is we would have to slice here, and then we'd get a washer in this spot. And then if I sliced across here perpendicularly, I'd get a disk in this spot. So the problem with doing this with the disk or washer method is you'd have to do two integrations. You'd have to, you're going to integrate in the y direction because you're slicing in the y direction. But you're going to have to go and integral from like some, say some C to D and some D to E. So instead of doing this as two separate integrals, I'd much prefer to do it as one integral. So we're going to use what's considered the shell method. So looking back at our function here, so the idea of doing this, this bounded region and then spin it around that y-axis is we can slice parallel to that axis and we get something that looks like this. So that's going to be our A of x essentially. So really when we're finding these volumes of revolution, it's always the integral of our slice. So when we spin this slice around this way as opposed to the slice being this way and spin it around, what we're going to get is we're going to get a cylinder. So I'm spinning this around. If I spun that around, you can see that slice is right here. And when I spin this thing around, you're going to get something that looks like this. So that being a cylinder. Now, really what I'm going to have to do is figure out what A of x is. Well, A of x is essentially the cross-sectional area of the cylinder. So if I kind of pull it out, slice it, open it up, what we know is cylinders, I guess the best thing I can show you is like my piece of paper here. If I have a cylinder, which is what looks like this, if I want to find its area, it's easier just to open it up and go ahead and find the area. So all I'm going to need is, its length and its height. Now what we know is the length of this thing is going to be the circumference of the circle, and the height will still be the height. So our A of x for here, our A of x is going to be, the area of this has to be, again, the length, which is going to be the circumference, so it's 2 pi r, that's the circumference, times the height. So what I know is if I want to find actually the volume of the blue thing, I'm going to have to integrate A of x from, the beginning of this cut all the way to the end of this cut. So you can see that this cut is actually going to be sliding in this x direction. So our formula for this volume is going to be equal to the integral from, say, a to b, now a being, this, and b being this, because this is going to be our start and stop, of our function, which is going to be, our A of x, which is 2 pi times the shell radius, multiplied by the shell height. Now, each one of these things will take function form or equation form. D, in this case, I'm sliding with respect to x, so we're going to go here. Now, if in this case, we're going to do a dx because this thing is sliding in the x direction. So what's interesting is when I'm doing the shell method, if I'm revolving about the y-axis, this is going to be with respect to dx. But if I'm revolving around the x-axis, you're going to see that your slice is going to be sliding in the y direction, so that'll become dy. So let me come up with an example that looks, somewhat similar to this, and we'll put this into play. So let me. All right, so this is going to be our example. We're going to find the value using cylindrical shells by revolving around the y-axis. So the region is going to be bounded by the square root of x, the x-axis, and then y equals 4. So let's put our curve in here. It's nice to know what it looks like. So what I know is y equals root x. I'll put this in blue. So root x is going to be this. And then the x-axis, which is going to be this. And then the the vertical line in y equals 4 is going to be right here, so this is going to be y equals 4. So we can see that the region, that our bounded region happens to be this piece right here. And what I'm going to do is I'm going to revolve this around, this color is very similar, but whatever. I'm going to revolve this around the y-axis, so around that axis. Okay, so in order to do this, what we need is we need our A of x, or our cross-sectional slice. Now, if we're using the shell method, our cross-section is going to be parallel to the axis of revolution, so this is going to be our cross-section. Now, I'm not going to draw the entire, blue thing spun around. All I need to know is A of x, and so a lot of times I like to draw that one particular shell here, so knowing that when I spin this around its axis, we're going to get that cylindrical shell. So we know that A of x is going to be 2 pi RH, where r is going to be the shell radius and h is going to be the shell height. So in order to find our volume is going to be equal to the integral. Well, let's look at the bounds first. So what I know is that this piece right here, this really is our slice right here. And that slice is going to start at 0, and then it's going to slide all the way to 4. So this is going to go from 0 to 4. Now, the height actually is kind of the easiest part. So let's do 2 pi. I'm going to put a blank there for the radius. And then we're going to talk about the height. Let's take care of the low-hanging fruit. So the height is going to be really kind of the subtraction of these two dots here. Now this dot, for instance, the top dot, this lives on that square root function, and this bottom dot lives on that y-axis. So really what we have to do is we just have to subtract the functions the dot lives on. So as we slide over here, the dot's going to be here, and then so on. So regardless, this is going to be root x minus 0, root x minus 0, and so on. So the height is going to be, our function value, which is going to be root x, so this one, and then minus on the other bound, which is going to be the x-axis, which is the same thing as y equals 0, so minus 0. I know it's a little redundant to say 0, but it does come in handy when we're trying to pay attention to heights that are a little more complicated. Now, the radius is kind of, I should say, arbitrary, because really when we look at this point is the function x comma root x. So if I look at this is the point x root x. That makes sense. So what we're doing is we're sliding from 0 to 4. So really x is all values arbitrary from 0 to 4. So we can see that that also makes this value x as well. So we can see that our radius is going to be that x, and our height is going to be the subtraction root x minus 0. So what we get here is this is going to be equal to the integral from 0 to 4 of 2 pi times, well, this 0 is gone, so I have x to the 1, x to the 1/2, so this is going to be x to the 3/2 dx. So we can pull out the 2 pi and we can integrate this. So this is 2 pi. Now the integral of x to the 3/2 is going to be x to the 5/2 divided by 5/2, or 2/5. Evaluated from 0 to 4. So 2 pi, let's plug in 2 times 4 to the 5/2 over 5 minus 2 times 0 to the 5/2 all over 5. So this is going to be equal to 2 pi times, so when I'm looking at rational powers, if it's possible, like 4 is a perfect square. And that 2 on the bottom really means square root. So I like to square root it first and power it second, like 5th power second. So the square root of 4 is 2, and 2 to the 5th is 32. So then this is going to be 2 times 32, which is going to be 64 all over 5. And then this, of course, is 0. So we're going to have 128 pi all over 5. All right. Let me do another example where the height is slightly more complicated. And we are going to spin it around, not just the y-axis, but let's also spin it around this axis. Actually, let's talk about the setup of this before I even do that. We might as well do it now. So what we did is we did this around the y-axis. But what if I asked, instead of the y-axis, what I said about x is equal to 4? What if I want to revolve around this? So if I want to revolve around x equals 4, well, this picture changes now. So on the same curve, we have this. This is going to be our bounded region. But now we want to spin this around this 4, so around here. So our shell is going to look slightly different. We know that it's going to be, still this is going to be our slice. So our bounds are still going to be from 0 to 4. because it's going to slide in this direction. But when we spin this around that axis, what we're going to get is we're going to get something that looks like this. So what we notice with this shell here is that the height's the same. You know, we're still taking this dot minus this dot for the height, so it's still going to be root x minus 0. The difference is our radius is now changed. So our volume here, our volume is going to be equal to the integral from 0 to 4, because that's the way this is sliding. And again, this is going to be dx, because it's sliding in the x direction. 2 pi, the radius, I'll get to that in a second. And then the height, we know it's going to be, again, this dot minus this dot, so root x minus 0. Now, it's this is still the point, you know, x comma root x, so that still makes this x here. But if I want to find its radius, well, the radius is going to be the distance between this point and this point. Now, this point is arbitrary. This is going to be x. So when I subtract this minus this, now we know bigger is going to be this way, smaller is going to be this way. So we know that the radius is going to be this dot, which is on the vertical axis 4, and then minus this dot, which is on, well, which is that arbitrary x. So this would be 4 minus x. And we can integrate this thing as well. So pull out the 2 pi now, might as well. Integral from 0 to 4 of this is going to be 4 root x minus x to the 3 halves dx. So this is going to be equal to 2 pi times, well, its integral is, this is 4 to the 1/2, so it's 4x to the 3 halves divided by 3 halves, or multiplied by 2/3. So this is going to become 8/3. Minus, we already did this, 2/5 x to the 5 halves. You know, evaluated from, I can do a bar. I can just write the 0 and 4 here. 0 to 4. So we know that we can plug this, this 4 and 2 pi times 8/3 times 4 to the 3 halves minus 2/5 times 4 to the 3 halves. And then I know when I plug 0 into both this expression, I'm just going to write 0 over here, of course. So that's going to be gone, so it's really only the upper bound. And then cleaning this up and hoping we don't make mistakes. So 2 pi times, square root of 4 is 2. 2 cubed is 8. So 8 times 8 is 64/3. So this is going to be 64/3 minus, it should be the same thing. Oops, I'm worried. So let's make sure square root of 4 is 2. 2 cubed is 8 times 2 is 16. Okay, we're okay here. What I was concerned with is getting a negative number here. It's kind of scared me. I didn't practice this one. So subtracting those, I guess I can do it on the calculator. Totally do it by hand. So let's go 64 times 5 minus 16 times 3 is going to be 272 over 15. 2 pi times 272 over 15, and there's no like term, so just times 2 is going to be 544 over 15. So 544 pi over 15. So really the major part of this example is kind of showing, you know, what about that? What if you don't spin around the y-axis? What does that new radius become? The antiderivatives are something you probably practiced plenty of by now. So let me do an example to where we spin around the y-axis, and that'll close us out. So let me pause it and set it up. I said y-axis, I meant x-axis. So we're going to revolve around the x-axis this time. We just did the y-axis. So this is going to be our bounds, and I'd like to draw it up. I think it's helpful for students to see that. So it's hard to draw these things in these forms. Most people don't see it this way. They usually see it in terms of y equals as opposed to x equals. They're not used to seeing it, their inverses quickly. So what I usually do is solve this for y. So this would be the square root of x is equal to y. Now, technically it's plus or minus. But what we know is that y is going to be greater than or equal to 0, so that means we're talking about positive y values. That's why this is positive root x. So we still have that square root of x here, so square root of x. Now, y equals negative x is the same thing as, negative x is equal to y, so that's this line here. And then this is going to be y is equal to 2, which happens to be, a horizontal line. So this is going to be, y equals 2. This is y equals root x. I'm going to write this in terms of what it was before. This is x equals y squared, and then this is x is equal to negative y. Now, they want only the positive y, so I'm going to get rid of this part, at least most of it. So our bounded region happens to be this right here. So when I want to revolve this around the x-axis, we're talking a revolution this way. So that means our slice, again, if we're doing the shell method, is going to be parallel to the axis, as opposed to the previous section. So now when I like to draw the shell, it helps me identify the radius and height. I recommend all my students do that. Draw the thing so you can see its geometry. Okay, so now we're trying to integrate this cross section, this a of x. So when I want to integrate this, in this case we can see that remember, even though I drew the shell, this thing is what's sliding. So that's going to slide from y equals 0 to y equals 2. So I can see I'm integrating with respect to y. So this is the integral from, let's say volume, is integrated from 0 to 2, dy over here, because I can see that that thing is sliding in this direction. 2 pi times the radius, and then times the height. Height, again, is kind of the low-hanging fruit. So the height is going to be, we can see the height is going to be the difference between these dots right here. Now remember, bigger, larger in the x, because you always have to do the larger number minus the smaller number. Larger in the x is this way, smaller is going to be this way. So it's going to be this x value, which is y squared. Notice that this distance is x, that's why we have x equals. So this is going to be y squared minus this one, which is going to be this x value, which is minus that negative y. I'm sorry, negative y. Remember, we're integrating with respect to y. That's why it makes sense that these things are y's. And again, this is the arbitrary point. Well, we have to solve this. This is actually, this is interesting. It's y squared comma y, if that makes sense. Because really, remember, we're kind of doing the inverses in a way. We're switching this around that. That this is the arbitrary y because we're bouncing from 0, but we're sliding from 0 to 2. So, this is sliding y equals 0 to y equals 2. So in between is some arbitrary y between 0 and 2. So that means its radius happens to be that arbitrary y. All right, so when we integrate this thing, this is going to be, well, first we simplify, and then we integrate. So 2 pi, this is the same thing as y squared plus y. So y times y squared is y cubed, and this is plus y. So y times plus y is going to be plus y squared dy. So 2 pi, antiderivative of y cubed is y to the 4th over 4, plus y cubed over 3, and we're going to evaluate this from 0 to 2. Okay, so plugging in the values and finishing this up. So the volume is going to be 2 pi times, we have 2 to the 4th over 4, plus 2 cubed over 3, minus, we can see when we, I'll write it out this time, because I have the room. But we can see when we plug in 0, this entire part of the expression is going to be 0. So 16 over 4, which is 4. So 2 pi, this would be 4 plus 8 thirds. So we're going to get let's finish this up. So this is going to be equal to. Let me pause and just verify I got everything good. Nope, I'm good with that. So this is going to be top and bottom by 3. So this is 12 thirds. So 12 thirds. So this is going to be 2 pi times 20 thirds. So 40 pi over 3. I just want to talk about when we revolve this, say around maybe y equals 2. They tend to pick like one of the upper bounds. So if I want to revolve this around y equals 2, just kind of do this. I'm only going to set up the integral. We're not going to integrate it. Same exact bounds here, 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 and here. What if I wanted to revolve this, say about y equals 2? So what's going to happen is our shell is still going to have the same height here Now we're going to spin it this way. So that means the radius is going to change as well. So, you know, the radius is going to be, I wish that dotted line was better, but it's going to be this dot minus this dot, knowing that this is y squared comma y. And then this dot is, you know, y equals 2. I'm going to put that cleaner. So that dot right there is y equals 2. So when we set this up, we know that the volume here is going to be equal to the integral from, well, still 0 to 2. It's still, you know, this piece is still sliding from 0 to 2. And 2 pi. Now the radius is going to be, well, the radius now is this, you know, this distance right here. So this distance being 2 and this distance being y. So this is going to be 2 minus y. And then we have the exact same height. So it's going to be, you know, your y squared minus y squared minus a minus y squared, which is going to be that dy. And then I'll leave that up to finish. So that is it. So please consider sharing and subscribing. Thank you.